Okay, again, I hope slides are okay. I hope everyone can hear me. So again, so let me start again by thanking you all for the, for accommodating this talk, even because again, Singapore, there's 12 hours time difference. And I do apologize for not really being able to attend the talks, but I mean, somehow, the conference starts 9 p.m. Singapore time. So it's very difficult. Okay, so in any case, today I'm talking about kind of some new things we are working on together with Seung from the National University of Singapore. So it's going to be about a non-commutative kind of extension of Lee-Seung's algorithms for NMF, but we're kind of tailoring it now for the positive semi-definite matrix factorization problem. Okay, so so this talk is going to be about an algorithm for PSD factorization. So let's kind of first start by defining what this problem is. So so in this setting, right? So we are giving as input, like a matrix X. It's a rectangular matrix M times N, and its entry-wise non-negative. So the entries of X are non-negative. Okay, so that's our input, and we are also given as input some kind of user-specified parameter R. Okay, so this R is some natural number, 2, 3, 4, 5, or your favorite natural number. So these are the two things we have, and what we're kind of asked to find is two families of PSD matrices. So we have the A's and the B's, and we have notice we have one of the A's for each of the rows of X, and we have one of the B's for each of the columns of N, for each of the columns of X. Okay, and these guys, they need to be positive semi-definite, and their size needs to be R times R. Okay, the user-specified parameter. Okay, and the main thing that we're asking from these two families of matrices is that for the IJ entry of matrix X, I want that to be equal to the tracing net product between AI and BJ. Okay, so that's the goal here. Okay, we're trying to find these two families of PSD matrices that somehow recover the entries of the matrix X. Okay, and again, R is fixed. Okay, it's some kind of someone has told me find a 5-dimensional PSD factorization. So that's what we're looking for, and now it's kind of easy to see that you can always if your R is like less than minimum number of rows and number of columns, you can always find the PSD factorization. That's not that difficult. Okay, but what is more difficult is to find the smallest R for which your matrix actually admits an R-dimensional PSD factorization, and that is known the PSD rank of X. Okay, it's a very nice, very cool quantity. And because it's kind of related to all kinds of stuff, and but my two kind of favorite applications. So the first one is that PSD factorizations in general, so they kind of capture the expressive power of semi-definite programs. Again, semi-definite programs, is just linear optimization over the cone of PSD matrices. Okay. And what I mean by that, there's some kind of this canonical correspondence that, if you have some polytope, you kind of associate a matrix to it, the so-called slack matrix. And then, PSD factorizations of the slack matrix, they give you a way to express your polytope as a projection of an affine slice of like a PSD cone, of the size of the PSD factorization. Okay, but somehow also there's some kind of very cool applications, also somehow very close, very interesting connections between PSD factorizations and somehow quantum information theory. Okay, so somehow again, if you have like some kind of matrix corresponding to a probability distribution, a PSD factorization, kind of gives you a way to realize this thing as some kind of quantum protocol. Okay, but again, I don't really have time to go into the details. But somehow, okay, this kind of PSD factorization is kind of relevant for kind of many areas. So both optimization and some information theory. And perhaps, the more geeky mathematical reason is that somehow PSD factorizations are like a non-commutative analog of non-negative matrix factorizations. And what are these? So what is a non-negative matrix factorization? So it's basically the same thing. It's kind of the same thing as we had before. We have like a matrix X, which is entry-wise non-negative, and some user-specified parameter R. But before we were trying to find PSD matrices that somehow were kind of realizing the X. But in the context of NMF, we are trying to find non-negative vectors, R-dimensional entry-wise non-negative vectors. And we have the A's and the B's. The A's kind of label the rows of X. The B's label the columns of X. And what we're asking from these vectors is that the AiBj entry of X is given by the inner product between AI and BJ. Okay, so this is like the NMF problem. And if you just think about it for a second, you kind of see that NMFs, they're basically very special PSD factorizations. And it's exactly the case when you kind of restrict the PSD factors, the AIs and the BJs, to be diagonal PSD matrices. okay? Because diagonal PSD matrices, they're nothing but non-negative vectors. So like, so NMF is basically it's like a special case of PSD factorizations. Okay, but somehow, but NMFs are somehow like, very, very popular. I would say much more popular compared to PSD factorizations. Okay, and they're basically, and the popularity is mostly because somehow you can kind of use them as a dimensionality reduction tool. Okay, and that kind of, brings about many cool applications, in areas like, document clustering, musical analysis, and many others. And the reason somehow why NMFs somehow come into play is somehow because they give this kind of very beautiful parts-based representations of your input data. Okay, so meaning that kind of you kind of explain your data by kind of adding, by kind of aggregating some, like a finite number of atoms. Okay. Now, again, this is kind of vague, and if time allows, I will kind of meditate a bit more on this. I will explain kind of more precisely what this means. But somehow, again, like NMF is like a very important problem, like beyond optimization, right? So it's very important in engineering, and has many applications. So okay, so somehow, okay, so we introduced the PSD factorization problem. So and somehow we kind of also introduced NMF and kind of realized that there's a special case of the PSD factorization problem. So now let's kind of slowly work towards kind of coming up with an algorithm for finding PSD factorizations. Okay, and so again, in this context, again, always remember that R, so the size of the PSD matrices, so that is fixed. Okay, so we have kind of made a choice. R is like 5 or 7 or 2 or whatever. Okay, so we have made a choice, and now we are trying to find an R-dimensional PSD factorization. So now, okay, so obviously, like the canonical starting point would just be to set up some kind of non-convex problem where you kind of minimize the the square loss over all the entries of your matrix. Okay, but of course, there's so much you can do with this, right? So, but again, like the standard thing you might do is you're going to try some kind of coordinate descent approach to solve this problem. So and probably the first thing you would try, if one showed you this, it would kind of do some kind of alternate optimization between the A's and the B's. Okay, so you kind of alternate between minimizing with respect to the A's. Okay, it's this n PSD matrices, A1 up to AN. Okay, so in this context, like in the first program here, the B's are fixed, and I'm just minimizing over the A's. And after I update my A's, I kind of minimize again over the B's. Okay, so just do kind of coordinate descent where I kind of have two blocks, the A's and the B's. So that would be kind of a natural thing to do, right? So okay, and again, like I don't want to be talking about both of these things, so let's just we're just going to focus on one of them because everything is entirely symmetric. Okay, so for concreteness, let's just say we have updated the AIs, so the AIs are like fine, and now we kind of need to worry about the BIs, the BJs. Okay, so I kind of need to solve this problem. Okay, and then you kind of stare at this for a second, and you basically realize that this guy is separable with respect to the BJs. Okay, so so in the end of the day, you basically just need to solve this for every for each, and here you only have one matrix variable. You have the BJs. Okay, and just to kind of to simplify notation, let's just omit the dependency on J, and I can just rewrite this as minimum x minus AB Euclidean norm squared. Okay, where here this is just simplifying notation, where this small x here is just the jth column of the matrix X. Okay, these are exactly all the entries that appear here, and script A is this linear mapping that you feed it a symmetric matrix of size R, and it spits out the inner products of your matrix B with A1, A2, and AN. Okay, with these fixed PSD matrices that we have kind of updated already in the previous step. Okay, and this norm is just the usual Euclidean norm. Okay, and okay, and again, hopefully you see that this is just notation. Okay, so this is just exactly the same as this program. Okay, so long story short, right? So doing this kind of coordinate descent approach, right? So this is the type of thing we need to solve. Okay, we need to solve this. I mean, at each iteration, we will need to solve an optimization problem of this form. Okay, so again, any questions, comments? Please just interrupt. Okay, feel free to interrupt. I'm not really keeping track of any of the chat. So okay, so now these like subproblems we encounter, they are convex. Okay, and in fact, this is what we would call like a convex quadratic SDP. Okay, But okay, I mean, they are convex, but we don't really have a closed form solution for these guys, right? So in the end of the day, if this was your subroutine and your coordinate descent, you would need to be using some kind of numerical optimization to solve this. Okay, right. So and somehow, there is some work out there, like dealing with, how to find PSD factorizations, and all of them, at least to the extent that I'm aware of, right? So, this is basically the starting point, okay, doing like, coordinate descent. So, and ending up with a problem that looks like this. And, in one case, like let's say in this paper by Vandele, Gillis and Gliner, they give two algorithms for this problem. So this was the first paper, right? So somehow the algorithms they give, they're kind of simple, right? So they give the first one is like a projected gradient method, where you take a gradient step and then you project back into the PSD cone. The second method is like a method that kind of also allows you to keep track of the rank of the PSD factors, okay, which is something I haven't really talked about, because okay, the idea here is that in the PSD factorization, so for the way I introduced the problem, I only fixed the size of the matrix. Okay, so the size is R, and that's fixed. It's like 5. But perhaps, and depending on the application you are looking at, you might also want to talk about the rank of the PSD factors. Okay, so like.
Can I ask you a question?
Yeah, go ahead. Yeah.
So you're saying this is a convex problem, but you're restricting the rank to be R, and it's still convex?
No, I haven't restricted the R. Right? I haven't restricted anything. Yeah. So when I say convexity, I'm talking about this problem here.
Oh, okay. Right? Sorry.
Yeah. So I'm just saying here. I'm just talking about the second algorithm here. Okay. I'm just saying. Okay. First of all, I'm saying that there are certain applications where besides. Okay, so you want to talk about you want to find the PSD factorization of size R, but you also want to say something about the rank of the PSD factors. Okay, so somehow low rank, and in this context, so basically you would go here and you would do like like the typical let's say Burel-Monteiro change of variables. So you replace B with like a UU transpose, where the intermediate dimension is the rank you care about. And this is exactly what they do here, okay? And then they basically solve that using coordinate descent with respect to all of these new variables that you introduce, okay? So that's what's happening here. And in like some kind of later papers by Favot, which works a lot on music applications in musical analysis, together with Vincent Tan and some other collaborators, they give some other algorithms for solving like this guy here, and these algorithms basically, they kind of just come from the fact that somehow they kind of realize that this is the type of thing that you get. Working in signal processing, when you work with problems like affine rank minimization, phase retrieval, and stuff like that, problems of this kind of type, these are the type of relaxation that you kind of end up with. Okay, so basically, they kind of look into the signal processing literature and they kind of dig out algorithms, for affine rank minimization and phase retrieval, and they kind of apply it to this problem. So these are like the kind of the existing things that are out there. So okay, so okay, so but now what we're going to do is going to be kind of different. Okay, so we're going to be using we're going to try to solve this problem, but using the majorization minimization approach, which I'm guessing some of you might have heard, maybe in the context of Gaussian mixtures. Probably that's a type of thing many people have probably seen. Okay, but in any case, like in one slide and without any pictures, so the MM approach, kind of on a very high level, okay, it's kind of a very generic method for kind of solving an optimization problem. So let's say you want to minimize f over some set script x. Okay, and if you want to apply the MM approach, what you need to find is you need to find the so-called auxiliary functions. So you need to find a family of auxiliary functions. So let's say one for every x in your domain. Okay, and the auxiliary functions, they need to satisfy the following two things. Okay, so the first one is what we call the domination property. So the auxiliary function just needs to lie entirely above your function f. Okay, so f of y is upper bounded by ux of y for every y. And the second thing is that at the specific point x, when you evaluate the auxiliary function at x, it needs to touch your function. Okay. so these are like the two things, okay, that you need. And as long as you have these two properties, then, I mean, essentially you kind of have an algorithm. But again, this is all like high level, right? So, and the algorithm is the following. It's like, you know, you have your kth iterate, which is xk. And then what you do is like you kind of set up the auxiliary function corresponding to xk. You minimize that, and that is the xk plus 1. Okay, so that is your new iterate. And I mean, and it's like, you know, it's kind of trivial to see that like if you do that, you know, this kind of update rule, you know, somehow along the trajectories of this update rule, if you will, so you know, the function f is non-increasing. Okay, so f of xk plus 1 is upper bounded by f of xk. Okay. So, okay, but again, like now, of course, now to make this work, you know, there's a lot of things here. Obviously here, you know, somehow the auxiliary functions need to be tractable in some way to be able to even kind of calculate, you know, this, you know, xk plus 1. Then there's also all kinds of convergence issues because, okay, so here we kind of see that f is non-increasing in value, but, you know, there's issues of, whether x is actually converging to a minimizer and stuff like that. But okay, but that's basically all I'm going to need from MM at the moment. Okay, so this is basically the definition. This is like the MM framework. Okay, it's just a generic framework. Okay, but and now I'm just going to show you how we can actually apply the MM approach to solve this kind of subproblem of interest that we encounter when we try to do PSD factorizations. Okay, so again, the first thing we need to do is, again, we need to find you know, an appropriate family of auxiliary functions, right? So that's the first thing we need to do, right, okay. So now, like the kind of the baby lemma, which is gonna kind of motivate somehow the core. I guess this is like step number 0, okay, which is going to lead us to the algorithm. Is that you know, if you could find like a linear mapping, you know, which is invertible. So that, you know, t is upper, you know, t minus A transpose A is positive. So in other words, you know, t is at least A transpose A in the PSD order. Okay, so then the function of interest is non-increasing with respect to this update rule. Okay, so and this is just very easy, and this just follows straight from the definition of the MM framework. Because, right, so, you know, this is our objective function, okay? So, and again, notice that I'm not worrying about PSD-ness at this stage. It's like I completely forgot about the PSD-ness, and I'm only like minimizing over symmetric matrices. So this is like unconstrained. So this is my objective function, and, you know, I'm just gonna do a Taylor expansion at B old, okay? So, and I'm just gonna get this identity because my function is a quadratic. And then, right, so, but then I am assuming that T is larger compared to A transpose A. And that's going to give me basically this inequality, okay? Okay, so essentially I just replace A transpose A with T here, which is fine because T is larger compared to A transpose A. And obviously, if you plug in B old for B, we have equality, okay? So these guys here, so this is really a valid family of auxiliary functions, okay? And again, if I just follow the recipe of the, you know, the MM approach, right? So the MM approach tells me that your new iterate is the minimizer of the auxiliary function at the old iterate. Okay, and of course that's something you can calculate, and this is what you're going to get. Okay, so again, if you had this t larger compared to A transpose A, so then again you can kind of bound the Taylor expansion, and you just minimize that, and this is the type of thing you get. Okay, hopefully this makes sense. Again, any questions, feel free to ask. But like, okay, but, you know, fine, that's like okay, but that's definitely not really what we want, because of course we are going for PSD-ness, right? I'm trying to find a PSD factorization of my matrix, and, you know, this type of update definitely is not going to guarantee any type of PSD-ness, right? So even if the old iterate B old was PSD, I mean, you know, there's just no way that B new is going to be PSD. Okay, so then the way we're going to try to enforce PSD-ness is by basically enforcing additional structure. So we're going to ask more things on the linear map T. Okay, so for now we only ask that T is larger compared to A transpose A in the lower order, but now we're going to ask 2 more things. And, you know, I mean, somehow kind of no surprise, we're going to basically ask that T kind of acts as like congruence with a positive definite matrix Q. So that's the first thing. That's the first additional kind of requirement. And the second requirement is that, you know, when I hit A transpose A B odds with T inverse, I want to get exactly B odds. Okay, so okay, so these are the two things. I mean, and they look technical, but I mean, somehow let's see where these things come from. So somehow they don't come from nowhere. They basically come from this update rule, which we had. Now again, remember T was linear, so I can kind of distribute T. And now, you know, you see that condition 3 basically says essentially that, you know, the first two terms here, they're going to cancel, they're equal to 0. And then, so the only thing that remains is that B nu is equal to T inverse acting on A transpose X. So this is what remains just by using 3. Okay, so if T satisfies 3, so then this is my updates. Okay, and now the last thing here to notice is that, you know, if you kind of work out what A transpose X is, well, A transpose X just basically forms this conic combination of the AIs. Okay, and remember the AIs, they have been updated in the previous step and they are PSD. So X, the vector X is supposed to be the jth column of the input matrix, which is non-negative. So this is a conic combination of positive semi-definite matrices. So it's itself, this is a PSD matrix. Okay, and then basically I have a PSD matrix and I hit it with T inverse, but I have assumed that T inverse kind of acts as congruence with a PD matrix, so PSDness is preserved, right? So somehow we are in good shape. If T satisfies these two additional properties, so then this is the update, and this update is PSD. Okay, so I hope that makes sense. Okay, so okay, and then basically the last thing is that, right, so again, kind of summarizing, right, so if we had a T that satisfies basically these three things, so then somehow we are in good shape, right? So essentially we have an MM algorithm. Okay, but then of course you might wonder, you know, is it, you know, can you actually find a T that kind of satisfies all of these things? And as it turns out, you know, not only you can, but it's also uniquely specified. Okay, and in the sense that so this Q here is going to be uniquely specified. Okay, so the Q matrix, and that's going to follow by I mean, essentially by the definition of the matrix geometric mean. Okay, which is, you know, I mean, algebraically this is the following, right? So if you have two positive definite matrices, so you know, this is the matrix geometric mean, okay, kind of algebraically. But I guess more relevant for us is the following definition, that if you kind of set up this kind of Riccati equation in the matrix variable X, again, C and D are positive definite, then you know, this beast here, the geometric mean, is the unique positive solution of this matrix equation. Okay. Right, so and then if you kind of, if I just go back one slide, right, so if you basically kind of combine these two things, right, so you'll see that you know, if you substitute T inverse with congruence with Q inverse, and then you use equation 3, you basically get that, you know, Q actually satisfies this equation here. Okay, or in other words, exactly by the unicity property of the geometric mean, you basically see that Q is nothing but you know, B odd inverse geometric mean A transpose A B odds. Okay, so Q is the matrix geometric mean of these two guys here. Okay, so okay, so that's yeah. Okay, yeah.
So you've got I guess yeah,
sorry.
Time is going.
Okay, sorry, my phone.
Take another 2-3 minutes, and maybe we'll.
Yeah, it's no worries. Yeah. So thanks. Okay, so Q is uniquely specified, and again, it's given by the mean between B old and A transpose A B olds. Okay, and basically that's basically essentially we have the algorithm, right? So and again, I mean, it's a bit of a mouthful, but all of this is saying this is just the formula, right? So it's just, you know, T inverse acting on A transpose X. If you remember that X is the jth column of your input matrix, and then if you also remember that we asked for T inverse to be of the form so this is going to be Q inverse acting on A transpose Y. Q inverse, and Q we kind of agree that is given by this geometric mean. So this is basically the algorithm. Okay, so this is the algorithm you get for updating your PSD matrices. Okay, and of course there is okay, so I don't really have time to go through the details, but of course there is something remaining to show, which is somehow the non-trivial part of the, I mean, I guess the technical part of the paper, is that you still need to show the domination property for this specific choice of Q. You get this mapping, Okay, and you do need to satisfy, again, A is fixed, and you do need to satisfy that the domination property, meaning that T is larger compared to A transpose A in the PSD order. Okay, and I mean that takes some work. But somehow you're gonna need to invoke like Lieb's concavity theorem and von Neumann stress inequality and patch things together in a nice way, and it kind of works out beautifully. Okay. Okay, and maybe some comments about this algorithm. Okay, it's like kind of simple and easy to implement, right? So this algorithm is really simple, right? Because I mean, it's basically it's just this formula, and it's just a matter of having a subroutine for calculating geometric means. So there's no projection on the PSD cone or anything like that, at least not explicitly. Okay, the PSDness of the additive is automatic. Okay, another cool thing is that if you actually look at fixed points of the update rule, they are basically points that satisfy the KKT conditions of the optimization problem we are trying to solve. And another very cool thing, which kind of we like a lot, and we are trying to explore in applications, is that this algorithm actually also respects block diagonal PSD factorizations. So if you need, meaning that if you initialize with a certain because you do need to initialize, and if you initialize with a certain block diagonal pattern, so this pattern is gonna kind of it's gonna remain as an invariant throughout the execution of this algorithm. Okay, so this is gonna kind of allow you to calculate block diagonal PSD factorizations, which are relevant also in quantum and for various reasons. Okay, and I don't know, and if I have like for my last slide, I guess, because I'm out of time, I'm not going to do Lee-Seung any justice. Lee-Seung's algorithm is somehow, it's like super useful and super widely used algorithm for calculating non-negative matrix factorizations. Okay, and this is like this is how it looks like. And again, it's kind of an MM algorithm, so it has like all the properties you're going to expect an MM algorithm to enjoy. Okay, but the cool thing is that if you basically just take our algorithm and you just specialize to diagonal PSD matrices, okay, so you just recover you recover Lee-Seung's algorithm. And again, I'm not doing Lee-Seung any justice here. I mean, this paper is like super important. It's like more than 10,000 citations. Okay, but again, special case of our algorithm, when you plug in diagonal PSD matrices, you do recover Lee-Seung. Okay. Okay, and we have some numerics. Somehow things are nice, but we're still kind of trying to apply this for more like more and more examples. Two things we are working on, and I mean, I guess maybe I focus on the second one, is that we have been able to kind of to extend this also for arbitrary symmetric cones. Okay, so if you were trying to find PSD factorization, I mean conic factorizations for symmetric cones, so then somehow things kind of work out. Although now you have to go through all the kind of Jordan algebra language. Okay, so that's all. I'm probably 1 or 2 minutes late, so I apologize for that. But thanks a lot, and please, if you have any questions, please go ahead.
Thank you very much.
Yeah,
for a very interesting talk, and I guess we have time for one quick question. We also will have time for questions after Anthony's talk, so hopefully you can stay around.
Yeah, no problem.
Yeah. Anybody have a quick question?
How would this compare to just off-the-shelf convex optimization?
I mean, I don't know. That's probably hard to say. I mean, you're probably gonna do you're gonna see extensive experiments when the abstract when the paper comes out. I mean, I guess the main difference I would say, because again, even you can ask the same question for NMF, right? So you could still be doing NMF by solving essentially non-negatively squares. Okay, but that's kind of a completely different beast, right? So it's going to be about interior point algorithms or whatever numerical subroutine you are using. I guess this has the advantage that it's just easy to implement. Even Lee-Seung, you just look at this, whatever, you just implement this. It's just, it's like 5 lines of code, and kind of runs well. Of course, you don't have very good theoretical guarantees. You only have the MM guarantees, whatever they are. Yeah, but I mean, I think this, I mean, the advantage here is simplicity.